Hello. So welcome to this part 5 series on differential amplifiers. In the previous video we looked at some LT-Spice simulation to build our intuition into differential amplifiers. Now we noticed that the differential amplifier would be more robust to saturation if we place the current source in between the two emitters tied together. So previously we realized that without the current source, these collector currents in these branches were free to move about depending on the base emitter voltage. But with the current source, if we lay emphasis on the fact that we are assuming IC is approximately equal to IE, then we can say that IC1 and IC2 should add up to the tail current IEE, which in this case is 2 milliamperes. So we can write this IC1 plus IC2 should be IEE, and which is very important. We saw how robust that made our device and preventing our device from running into saturation. Okay, so we are going to do a quick study and see what happens here. So if that's the case, then what will be the output voltage at this node? So that's going to be our VCC. We know to be 5 volts, but I want to use the variables. So VCC minus, now what's the value of IC? IC should be half of IE. So that's IEE over 2 and times RC. Okay, so we could use this to determine the headroom easily. In this case, our voltage being 5, then assuming I wanted the voltage to rest at 2.5 volt, then I set the current source to be 5 milliamperes. Then I know I'm going to get 2.5 milliamperes and 2.5 milliamperes here, regardless of the base emitter voltage that I have. And that means that when there's no signal coming in, the voltage at the output will rest in the middle of the available voltage. So the swing will have enough room both up and down. If you are not familiar with headroom, you have to go back and review the video on voltage headroom. All right. So okay, so I touched my microphone. Just want to be sure it's still okay. All right. So that's one thing that we've noticed, and you've also seen that this voltage would be exactly the same as that one. So then the differential output, if I call this Vx and I call this node Vy, the differential output, which is Vx minus Vy, should be equal to 0. We also place some noise in the VCC. In the very first video, we explained how through rectification, ripple voltage will be introduced into the available DC voltage that we are using as our VCC. And we saw how each side had noise, but the differential output had no noise. But that only happened when we put a differential input. So I explained the differential input in the second video. If you're not sure, you can go and watch. So this time around, the microphone signal that was introduced was plus V0 sine omega and omega t, and here we had V0 sine omega plus omega t plus a phase shift of pi or 180 degrees, or you just put the negative in front of that as we did, and we saw the differential output. So now we want to do a quick study on what would happen if we changed the voltages here So this time around, we no longer have a common mode voltage. I'm going to change the voltage at the input and see what is expected to happen. So assuming I did this, okay, so now we are going to tie the two to the current source, because we know that gives us a robust differential amplifier. Okay, so this Q1 and Q2. I might also lay emphasis on symmetry. So we expect R and R, the RCs to be the same, the two Qs to be the same, and that's how to best construct a differential amplifier. All right, so supposing the voltage here is 2 volts, at least we know that's fine, and this also 2 volts, we know what will happen. And we had IEE, then the current here would remain IEE over 2, and the current here would also remain IEE over 2. All right, that's fine. But what if I make this 1 volt and this 2 volts? Now the common mode voltages are no longer the same, so we are just seeing what happens to the circuit. Okay, so in drawing the analysis, we will just assume the base emitter voltage, which is always in the range 0.5 to 0.8. Let's assume 0.7. So if this voltage is at 2 volts and this voltage is at 0.7, then the voltage at this node has to be 1.3 to obey Kirchhoff's voltage law. Now if this voltage is at 1.3, then it means that the emitter and the base means Q2 has to be off, because the emitter is more positive, because this is an NPN device, and you have the emitter being more positive than the base, meaning Q2 would have to be off. And if Q2 is off, which means no current can flow through here, so IC2 would have to be 0. And if IC2 is 0, what's going to be the voltage at this point? The voltage at this point has to be VCC minus IC2 RC. But since IC2 is 0, all this is 0, and means VCC should also be equal to 0. And the rule that IC1 plus IC2 should be equal to IEE still remains. So that means IC1 would have to be equal to IEE. And in that case, we are going to have all of IEE flowing through this branch. So what's going to be the voltage here? The voltage is going to be VCC minus IEE rather than IEE over 2 by RC. That's going to be the voltage at the node VX. So this is very important concept that we need to know to understand how the bipolar amplifier behaves. So I'll end this video here. See you later.